Now with motion in a straight line, definitions and graphs. Again, I think you've done some of these already. Oh, I think you've done all of this already in the first term, but in a physics way, not in a maths way. So probably very similar. Right, so we're on page 178 here, and lesson 72. And right, I'll just carry on. So we can use these terms to describe location and movement. The terms are down here. Okay, so we've got position is a vector, the distance and direction from the origin. Displacement is a vector, which is the change of position. Distance is a scalar, which is the magnitude or size of the displacement. Velocity is a vector, which is the rate of change of displacement. And speed is a scalar, the magnitude of velocity. Okay, example. If a particle starts at the origin and then moves 4 units in the positive x direction, followed by 6 in the negative x direction, it's actually moved 10 units, 4 plus 6. But the resulting displacement is minus 2, because the displacement, if you base it against the origin, it's gone 4 that way, but then 6 back that way. So that's 6, so it's going to be minus 2 overall. So it is important to distinguish between displacement and distance. So I always think if I start from my home and walk to work and back again, I've walked about 3 miles, but my displacement is 0 because I'm back where I've started from. Okay. Similarly, it's important to distinguish between the average velocity during motion and the average speed during motion. Average velocity is the resulting displacement over total time. Okay, so that just, and here look, that's just the final displacement. So in this example here, it'd be minus 2 divided by the time taken to do it. Whereas the average speed is the total distance that you travel over the total time. So you can see they're going to be different. If this journey in this example here took 10 seconds, then the average velocity is going to be minus 2 divided by 10, minus 0.2. Whereas this one is going to be 1 metres per second. Okay, this is going to be minus 0.2 metres per second. So it's got to be different, be sure. Right, example 1. A particle starts at the origin, moves 12 metres in the positive x direction for 6 seconds, followed by 15 metres in the negative x direction for 5 seconds. Sketch displacement time. Find displacement of velocity for the first 6 seconds and the final 5 seconds. Find the resultant displacement, the average velocity and the average speed. Okay, I wonder if I can copy this across to the next page. Copy. Let's put that up there. Nope. I'll just try and do this because it'll help if I can do it. I'll just leave it. I'll just flick backwards and forwards just so that we don't waste lots of time. Right, sketch a displacement time graph of the motion. Right, so what we've got here is okay, so it starts at the origin, moves 12 in the positive x direction. So it starts here in how many seconds? In 6 seconds. 1, 2, 3, 4, 5, 6. And then it moves in 5 seconds. 1, 2, 3, 4, 5. So that's going to be enough times there. 12, 2, 4, 6. So that's our first one there, and that's our final one. And it's got to move 12, 2, 4, 6, 8, 10, 12. And we just need a few under here. Okay. So we can say that's the first one. That's the first motion. After 6 seconds, it's gone forwards 12 metres. This is the displacement, this axis here. Displacement in metres. This is the time in seconds. So after 6 seconds, now it goes 15 metres down at the bottom here, 15 metres in the negative x direction for 5 seconds. Okay, so it's got to go back. So go in the 5 seconds, this is 12. 12 brings you back to the axis, so we actually want 15. So we've just got to go slightly below, like so. Okay, does that make sense? So this here, oh, this is quite fiddly, so I'm just going to just change this here a little bit. So look, that's -3. Okay, and that's -3 has come from the 12 to the -3 is 15. So the first journey is 12 that way. The second journey is 15 back the other way. So it goes up to 12 and then down to -3. Okay, so there's the diagram. Find the displacement and velocity for the first 6 seconds. So number 1, the first 6 seconds. The displacement, that one is straightforward. The displacement is 12 metres and the velocity is 12 divided by 2. 12 divided by 6, I'm thinking on again. 12 divided by 6, which is 2 metres per second. And for the final 5 seconds, so when we talk about just the final 5 seconds, we've got to say in that particular time span, displacement is -50 metres. So the velocity is -15 divided by 5, which is -3 metres per second. Okay. When we do the resulting displacement in part 2, is 12 minus 15, which is -3 metres, and that's because it does 12 for the first part and then takes away 15. The average velocity, this is it's -3 divided by 11 metres per second. The average speed is 12 plus 15 divided by 11, which is 2 5/11 metres per second. Okay, so the speed doesn't take into account that the 15 is in the opposite direction to the 12. Okay. Right, next section. We can also draw a velocity time graph. Draw a diagram of a velocity time graph such that when t equals 0, v is u, and when t equals t, v equals v. Right, so this is the velocity here. When they say like a velocity time graph like that, so it's v first, that's on the vertical axis. The second one is on the horizontal axis. Okay, so when t equals 0, v is u. when t is equals to t, v is equals to v. Okay, and that's what we want there. And it's made a trapezium. Okay, if you remember a trapezium, we've got parallel sides. Trapezium doesn't necessarily have to have a right angle, but this one does have. It could be like this, but this one has got a right angle there. So if velocity changes from u to v, here look, so it goes from u to v, the gradient is the change in v minus u over t. So it's v minus u over t, metres per second. So it's the rate of change of velocity, which is acceleration. So acceleration is the rate of change of velocity, and it's the gradient of a velocity time graph is the acceleration. Okay, because that's a measure of how the velocity is changing. Acceleration is change in velocity over time, v minus u over t. Okay, the shaded area, let's shade this, I didn't shade it. Okay, if you've got the area on a velocity time graph, so it's metres per second velocity times seconds for time. You see that the seconds cancel out, so it's metres. So the area is going to be the displacement. And what they've got here, the shaded area, this is the area of a trapezium, half u plus v times t. So it's half of this height, which is u, and that height, which is v. Times t, which is this distance across the bottom here. Okay, so it's the average velocity, half of u plus v times t times time is the displacement. And the area between the velocity time graph and the time axis is the displacement. Okay, so I like it when we've got an example. Right, okay, example 2. A particle starts at the origin. It undergoes a constant acceleration for 15 seconds until it has a velocity of 6 metres per second. Look, I'm glad it says here. I've just quickly read on sketch the velocity time graph. I'm going to do that as I go along. It starts at the origin. A constant acceleration for 15 seconds. I don't know where that is, but let's say it's there. Okay. Until it has a velocity of 6 here. Constant means it's got a straight line. So that's the velocity, and they're metres per second. And that's seconds. Velocity of 6. Velocity then decreases with constant deceleration until time 35 seconds. So that's 30, so a little bit further on. So that's 35. Particle has a velocity of -4. Okay, so I want to go below here. And it's about 2/3 of that there, -4. Like that. Okay. Negative acceleration is sometimes called deceleration. After 27 seconds, the velocity becomes negative. So that means that there, oops, just wanted to do that a little bit there. So that one there, that's the 27 there. Okay, that's velocity 0. So velocity then decreases with constant deceleration until time 35 seconds when yeah, I've done that bit. Okay, after 27 seconds, the velocity becomes negative. The acceleration is negative, but the speed increases. Okay, so that means at this time 27, the speed is 0. After that, it starts to pick up speed again because it's going in the negative direction, but it's picking up speed. -4. Right, calculate the acceleration during the first 15 seconds. So part B, 1. The acceleration in the first 15 seconds. So it's the change in velocity, 6 minus 0 divided by time, which is 0.4 meters per second squared. Okay, the remaining 20 seconds. In the remaining 20 seconds. Okay, so it's the change in velocity. So it ends at -4 and starts at 6 divided by 20. So it's minus 0.5 meters per second squared. Okay, it's minus 10 over 20. That's B. Part C, the resulting displacement. Well, in the first 15 seconds, in fact, we can change that. We don't need to do it in 15 seconds. In the first 27 seconds, it's moving forwards. Particle moves forwards in the first 27 seconds. And the displacement is the area. Okay, so even though its velocity is decreasing, it's still moving forwards, it's just slowing down. So I'm trying to think how it might be. It's like rolling up a hill. If you push something up a hill, it will keep going up, but its velocity would slow down to the point where it gets down to 0 before it comes back down again. Which doesn't quite match this. It matches this part here. So this part is like if you give it an initial velocity up a hill, it will decrease to 0 and then come back down again, which is what's going on this bit here. So the particle moves forwards in the first, and the displacement, C continued, just here. The area of that triangle, 1/2 base times height, 1/2 times 27 times 6. So it's 3 times 27, 81 meters. And that's the displacement. Displacement is 1/2 base times height. Okay, the total distance travelled. So it's the 81 meters, and then in the going backwards, so this is C part 1. This second triangle here, this is the area. This area is the displacement when the particle starts returning to itself. So that area shade, I could call it shaded area. (35 minus 27 divided by half base. So that's the half base times the height times 4, which is 4 times 4, which is 16 metres. Okay. Now it's moving backwards in those last 8 seconds, and that's because the velocities turn from positive to negative. So the resulting displacement, so that's the forward displacement, if you like there. The resulting displacement is 81, take away 16, which is 65 metres. Hope that makes sense. So that's the forwards displacement there, that bit. And that's the backwards displacement there. Okay. Right, the total distance travelled. Is that... Sorry, that is part 1. I'm not straight. The total distance is 65 metres plus 16 metres. No, it's not. It's 81 metres. Oops. Here we are. Sorry about that. The total distance is... It starts off, it goes 81 metres forwards plus 16 metres backwards. So it's 97 metres in total. Okay. And D, sketch the corresponding displacement time graph. Where can I do that? I'll put a new page in, plus a page here. Blank page. Okay, the corresponding displacement time is since the time. This is S is the unit that we use for S. Okay, so if we look at the diagram, the first 15 seconds, it's the area at that point, at the 15 seconds, is a half times 15, half base times height, which is 45 metres. Okay, so it goes to 45 metres first of all, and that is in the 15 seconds. Okay, and then in the next 12 seconds here, look, from 15 to 27, it's still increasing its displacement, but it's slowing down. It's going forwards, but we've not as much. But it is slowing down. Like I said, whoops, wrong thing there. So we've got to go there. Okay, and that's going to be at 27 seconds there. And at that point there, after 20 seconds, that's when it's done to 65 metres. And then after the 65, it starts to come back on itself by 16 metres. Actually, it's not, sorry, that one is 81. 65 is the very final one. So that one is the 81 metres, and then it comes back 65 metres. Right, so in there, that bit there, that's 81 metres forwards, 16 metres backwards. There we are. So that's across there. That's at 35 seconds. Okay. Right. Example 3 now. Draw an acceleration time graph for the following scenario. An object undergoes a constant acceleration of 2 metres per second for 2 seconds. So if we're going to have acceleration time, 2 metres per second for 2 seconds. Has 0 acceleration for another 2 seconds, and it experiences an acceleration of -4 for 3 seconds. Okay. By sketching the velocity time graph, well, that's acceleration time. So now we've got to do velocity time graph as well. Okay, so let's just put these marks on here because these will be helpful. 7, 4, 2. So it undergoes a constant acceleration of 2 metres per second squared for 2 seconds. So it starts off at 0. Well, does it start at 0? I've just looked at the book, and it says it starts at 2. At the start of the period, I missed a bit off there, yeah. At the start of the period, velocity equals 2 metres per second. Right, so it starts off at 2 metres per second. And then it means that, and then it undergoes a constant acceleration of 2 metres per second squared for 2 seconds. So that means after 1 second, it's at 4, because it goes, this bit here, this means that the velocity increases by 2 every second. It's 2 metres per second every second. So at 2, it goes to 6. Okay. 0 acceleration means that it stays at the same velocity for 2 seconds. And then it experiences an acceleration of -4 metres per second every second for 3 seconds. So it's 4, 5, 6. So it goes down by 4. So at 5 seconds, it's going to have gone down from 6 to 2. At 6 seconds, it's going to be at -2. And then at 7 seconds, it's going to be at -5. Because it's got to go down by 3. Okay, so it's going to look something like this. Okay, so I hope you can understand how I managed to piece that together. Calculate the resulting displacement of the object and the total distance travelled. Okay, so what we need to do is work out the area of these graphs, area underneath this are the shapes of this graph. Okay, and that's -5 there. So this one, we'll call this shape A, shape B, shape C, shape D. Right, A is a trapezium, so that's half of 2 plus 6 times 2, which is 8 metres. B is a rectangle, so that's going to be 2 times 6, which is 12 metres. C is a triangle, that's half. Base, now there is not drawn very accurately, but it... sorry, that's -6, not -5, because it goes down by -4. The acceleration is -4, so it's got to go from 6 to 2 to -2 to -6. So these two are actually symmetrical shapes. Yeah. So it's a half base times height, which is 6. That's 4.5 metres. Okay. And then D is also going to be a half of 1.5 times 6, which is 4.5 metres. Okay, so the displacement is going to be the forwards, the A plus B plus C, 8 plus 12 plus 4.5. But then we've got to take off the 4.5, which is where it goes backwards once it goes below the time axis. So it's going to be 20 metres. But the distance is 8 plus 12 plus 4.5 plus 4.5, which is 29 metres. Okay.